Okay, today we are doing some more trig identities. The ones from today will be called Pythagorean trig identities because we are going to use the Pythagorean theorem to prove them. The first three, we are actually going to prove the identities. So you need to copy the proofs down. You are responsible for using the Pythagorean theorem to get these three if I ask you that on a problem set or on a test. So everybody plan to copy these down. You are only going to need to memorize one of the 9 identities we will have by the time we are finished going through these. So the first one we want to prove is the most important. Sine squared theta plus cosine squared theta equals 1. That is the one we need to memorize. Sine squared plus cosine squared is 1. We're going to be using that a lot. Since it has squares in it, we are going to use the Pythagorean theorem to prove that sine squared plus cosine squared is 1. So if I'm going to use Pythagorean theorem, that means I need to have a right triangle. And I've got sine and cosine in this identity, so I want a right triangle so I can use SOHCAHTOA. So the first part of my proof, I am going to do a little column or table off on the side with 3 things in it that I will be using once I start my actual proof over on the right side. So I've got my right triangle. Since I have theta in my identity, I need to label one of my angles with a theta. Since it is the Pythagorean theorem, I need to label my sides as well. And I could use any letters that I wanted to, M, T, Q, but I'm going to stick with A, B, and C because that's what I'm used to with Pythagorean theorem. So one of the things I know from this triangle is A squared plus B squared is C squared. There's my Pythagorean theorem. Since I'm doing a proof that has sine and cosine in it, I'm going to write down what sine and cosine have to be. I've got this right triangle, so I can use SOHCAHTOA to write down a ratio of some letters for each of these. So Mia, what letters would I have for sine of theta on this triangle? So opposite over hypotenuse would be A over C. And Gavin, what about cosine? B over C. So those 3 things I'm going to end up using in my proof. To do my proof, I write down the longer side just like it is. Sine squared theta plus cosine squared theta equals. Now I'm going to start using these. I know what sine is, so this is going to be sine over sine is going to be A over C times A over C. And I just wrote down that cosine is B over C, so cosine times cosine is B over C times B over C. And A over C times A over C is A squared over C squared. Similarly, the second part is B squared over C squared. So now I have 2 fractions. And what do I have that's good because I'm adding fractions? I've got the common denominator, so I'm going to write that as A squared plus B squared over that common denominator. And what do I know from the 3 things that I wrote down on the left, Gina, about that numerator now? What do I know about A squared plus B squared? It equals C squared. So now I have C squared over C squared, which is, everybody? So we just proved that identity. Now let's think, does that make sense to us in another way? We know about unit circles, right? Better say yes. We know the radius on a unit circle is 1. That's what it means to be a unit circle. When we have a unit circle, we know something about the x and the y coordinates in terms of sine and cosine, right? So if I have some line like this red one, not one of the ones that I've memorized, but just any old angle in there, it's got an x and a y to get up to this point on the circumference of the circle. What's the x coordinate in terms of trig? Cosine, and the y coordinate sine. Over here on the blue one, the x would be a negative, but that would be the cosine of that angle and the sine of that angle. So since it's a right triangle, x squared plus y squared would be 1. But that means cosine squared plus sine squared would be 1, which is what we just proved. Questions on that one? Okay, second proof that you need to be able to do. I don't have sine squared or cosine squared anymore. Now I have cotangent squared and cosecant squared. Still got squares, so I'm still going to do this based off of the Pythagorean theorem. So I draw my right triangle. I label one of the angles theta to match the theta that I have in what I'm trying to prove. And I label the sides of the triangle so that I can write down a squared plus b squared equals c squared. This time the trig functions in the proof that I want to do are cotangent and cosecant. I need to use SOHCAHTOA, but cotangent is not part of SOHCAHTOA. But cotangent is the reciprocal of what? So cotangent is the reciprocal of tangent. So that means the tangent upside down. SOHCAHTOA says tangent is opposite over adjacent. So upside down, the reciprocal, I need adjacent over opposite. So Casey, what would adjacent over opposite be? So B over A. Morgan, what's cosecant the reciprocal of? And sine is what? Opposite, adjacent. How does sine go? Opposite over hypotenuse. So reciprocal is hypotenuse over opposite. So what letters will that be, Elizabeth? So now I have those three things I can use in my proof. Just like before, we'll start with the longer side, and then we'll start substituting. 1 plus cotangent squared of theta equals 1 plus cotangent is b over a. So I'm going to have b over a times b over a, which means I have 1 plus b squared over a squared. Got a fraction. Billy, I want to add that fraction, so what do I need to have? What? I've got a fraction. I'm trying to add. What do I have to do? Got to get a common denominator. So this 1 needs to be a squared over a squared. So now my common denominator is a squared. My numerator is a squared plus b squared. Shane, what do I use from my three things that I wrote down to begin with that'll help me simplify this? So that Pythagorean part, that numerator is now c squared. Did I do this right? So c squared over a squared. Wait a minute. What do I do with that? Oh, wait a minute. I've got a c over a, don't I? I've got c over a. So that is the same as c over a times c over a. But c over a, we just said, is cosecant. But I had cosecant times cosecant, so cosecant squared. Is that what we were trying to get to? So we've proven that one. And yes, I'm kind of trying to model some of the thinking that I expect you guys will be doing as you work through these. Wait a minute, is that what I really wanted? Does that help me or not? That will be part of doing proofs. Okay, the last Pythagorean trig identity that we're going to prove, and then we'll just start doing other random trig identities using these things. Last one is tan squared theta plus 1 is secant squared of theta. So once again, we draw our triangle, we label an angle theta, we label our sides, and then we're still going to use Pythagorean theorem, a squared plus b squared is c squared. This proof has tangent in it, and it has secant in it. So I'm going to try to write those down with a, b, and c. So Ava, what do I need for tangent of theta? So SOHCAHTOA, so I need opposite over adjacent, so a over b. Secant is not part of SOHCAHTOA, so Giselle, secant is reciprocal of what? So reciprocal of cosine, and cosine is Hypotenuse, what? Adjacent, opposite, hope. Adjacent over hypotenuse, so the reciprocal is hypotenuse over adjacent, so what does that mean for theta? And now we're going to try to do our proof using those three things. Begin with the longer side, tan squared theta plus 1 equals. Well, we know tangent is a over b, so we're going to change tangent times tangent to a over b times a over b. Then that means we have a squared over b squared plus 1. Once again, I am adding. So Sydney, what do I need to do now? So I need to get that common denominator, so I'll multiply this 1 by b squared over b squared. So I have a squared plus b squared over b squared. A squared plus b squared is c squared, so the numerator is now c squared. I've got c squared over b squared, but that is c over b times c over b. And what did we say c over b is, everybody? So this would be secant squared of theta. And that's what we wanted. So everybody good with how you prove the three basic Pythagorean trig identities? Okay, let's put these three in your formula list. These are the ones we just proved. The only one of the 9 identities today you need to memorize is sine squared plus cosine squared is 1. And yes, I say it all the time just like that without an argument. Anytime you write it in a proof, you have to have theta or x or a or whatever your argument is. If it's scratch work or you're just saying it out loud, you can skip the argument. Now, I say quickly derive these last two. By that, I do not mean on a test you have to go through what we just did with proving it. On a test, you're going to have your one that you memorize, and as soon as you get to a problem that has any one of these trig things squared, in a corner of your test paper, you're going to do your scratch work. Sine squared plus cosine squared is 1. I don't care if you've got arguments in that scratch work in the corner or not. In the real problem, yes. I need an identity that has cotangent in it. Can sine or cosine be a numerator for cotangent? Cosine could. What do I need cosine over to be cotangent? So if I divided that term by sine squared, I'd have a cotangent squared right there. If I divide that term by sine squared, I need to divide all of the terms by sine squared. Sine squared over sine squared would be 1. Cosine squared over sine squared would be cotangent squared. And 1 over sine squared would be the cosecant squared that you see over here on the right. So you memorize sine squared plus cosine squared equals 1. You use that. If you have cotangent squared or secant squared or tangent squared or cosecant squared, you write that down and you derive the other one. Let's suppose we got to a problem that had secant squared in it. So we write down sine squared plus cosine squared equals 1. What do I know about secant in terms of sine and cosine? Secant is what? Come on, you guys know. What's it the reciprocal of? So secant is 1 over cosine, right? So out of these three things, sine squared over isn't going to give me secant squared. Cosine squared over something won't. But if I divided this part by 1 over cosine squared, I'd have my secant squared. And then if I divide that, I need to divide each of these. So another identity that I'm not going to have in that corner of my test paper as some scratch work is sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. So do you see how you can just remember sine squared plus cosine squared is 1 and very quickly get these other ones? Okay, that gets us up to, we have 3 identities. We know how to memorize 1 and get the other 2. Now the way to get 6 more from those 3. Very easy. What if I had Secant squared minus 1. What if I subtracted 1 from both sides? What would secant squared minus 1 be? Tangent squared. What if I did 1 minus sine squared? Is that what we get when we subtract sine squared from both sides of this one? So that would be cosine squared. What if I had one that said 1 plus cosine squared? Can I get that from any of these three? No. I can get 1 minus cosine squared, but not 1 plus cosine squared. So 1 plus cosine squared, we don't know what in the world that's equal to. So here are your 9 identities. You don't need to write them down again. You don't need to have all of these in your formulas, just those 3 basic ones. Memorize sine squared plus cosine squared is 1. Know you can divide and get the other 2. Know you can isolate any one of the other things to get these other 6. Questions there? Okay, now we're going to have some new homework type problems. We're going to go through 4 of these proving trig identity problems, and they're messier than the ones you've been able to do up to now, because now you have the Pythagorean trig identities that you can use, and you still have what you were using before with rewriting in terms of sine and cosine for the most part. So can we all agree that the left side of this one is the messier one? We're going to write that down exactly like it is. Secant squared x minus tan squared x over 1 plus cotangent squared x. Okay, now I'm going to imagine this is on a test, so I can't look at the formula pages and the notes that I've just written down. But what's the identity you've memorized? Sine squared plus cosine squared equals 1, so I'm going to find a spot. I'm not going to worry even about my arguments in it. I'm going to write down sine squared plus cosine squared is 1. And I look at this and I see, you know, I need a secant squared in there. So can I get a secant squared out of what I just wrote down here on my scratch work? How can I divide by, Holly, and have a secant squared in there? If I divide everything by cosine squared, I'll have a secant squared right there, right? So that means my scratch work reminds me that sine over cosine is, and those were squared, so tan squared plus 1 is secant squared. Is that going to help me with that numerator at all? Okay, let me rephrase that. How does that help me with the numerator? What do I do with that to be able to simplify my numerator? Elizabeth?
Could you isolate the 1 and say secant squared minus tan squared equals 1?
I could look at this and say, hey, you know, if I isolate the 1, I have secant squared minus tangent squared, which is exactly what I have here, so I can just change that numerator to 1. Was anybody thinking, oh, I've got secant squared is tan squared plus 1, so I just change that first part to tan squared plus 1? That's okay too, because if we did that, we'd have tan squared plus 1 minus tan squared, and the tan squares would cancel, and we'd have 1. Denominator, it also has something squared in it. Anytime I have trig squared, I'm going to think Pythagorean trig identities. Okay, I wrote down sine squared plus cosine squared before. This does not get me anything with cotangent squared. So I haven't written this down yet on my test paper, so I'm going to write this down again. Sine squared plus cosine squared is 1. Can I divide by something different than cosine squared and get another identity? What was the other thing we divided by, Evan? If we divide everything by sine squared, I will end up with a cotangent squared here for this term. And in fact, I will end up with 1 plus cotangent squared is what? What's 1 over sine? So cosecant squared. So what does that mean for my denominator? 1 plus cotangent squared is, it's not what I needed. I didn't need 1 over cosecant, I needed sine. How do I get from what I've got to sine squared now? Come on, somebody knows. This one's easy. Flip it. They're reciprocals. So 1 over cosecant is sine. And since they're squared, that is equal to sine squared. And we have our proof. That one makes sense. So good news is that makes sense. Bad news is the last 3 are a little bit more complicated than this. But you guys can do it. I don't know what the heck I'm going to do with this one. I don't have any squares in that thing. I don't know why this isn't a lesson on Pythagorean trig identities. I'm not even sure which side is more complicated than the other. So I think I'll just arbitrarily say I'm going to start with the left. 1 over the tangent of A plus the tangent of A. And, you know, I am adding fractions again. One of them's a fraction. Catalina, what do I have to do anytime I'm adding something with fractions? Got to get a common denominator. So first one seems okay. So I am going to just add in that I'm going to multiply this one by tan A over tan A so I can have a common denominator. So now everything has a denominator of tan A. And the first numerator is just 1. But the second numerator is now tan A plus tan A, so tan squared of A. Now I've got something squared, so now I am thinking maybe it does have something to do with Pythagorean trig identities. If this is another problem on that same test, I've already written my 2 identities down in a corner of my test, so I'm going to look back at that test corner, and I know that I have tan squared plus 1 is secant squared, and 1 plus cotangent squared is cosecant squared, and this one I had a tan squared in it after I multiplied by tan A over tan A. So I'm going to look at that corner of my test paper. Tan squared plus 1 is secant squared. Will that help us on this problem? Callum, you're nodding yes, so what do I need to do? So secant squared of A over tangent of A. Okay, now we're going to look at, what are we trying to get to? We want to get secant A cosecant A. Do I have either part of that now? I've got a secant in there, so I want to keep that secant. I don't want to get rid of it. So I'm going to say that means I have the secant of A times, and then if I pull that out, that leaves the other secant of A over the tangent of A. Okay, no more squares, so I'm not doing Pythagorean trig identities. What's the other method you've been using on quite a few homework problems already? When you've got a tangent in there or a secant in there, what do you change it to? Change them to sines and cosines, right? So let's change both of those. Let's keep the first secant A like it is, because we know we want to hold on to that. But the other secant is, I think you guys just said 1 over the cosine. And tangent is what? Ariel, what's tangent? So sine over cosine. We can say it's sine over cosine, but we really need to write sine A over cosine A. So now I have secant A times a complex fraction. What do I do to clean up a complex fraction? What? Okay, 2 ways of thinking about it. I could say this is 1 fraction for the numerator divided by a second fraction for the denominator. So when I divide fractions, I keep the first one and multiply by the second one flipped. Or I could say these both, I could look at these denominators inside the complex fraction, and I could multiply the main numerator and the main denominator each by that least common denominator. So my cosines cancel, and now I've just got a 1, and my cosines cancel, and I have a sine. And that's getting kind of messy on me, so let me write that down so I can see what I'm working with. Secant A times 1 over the sine of A. Is that what I wanted? I don't remember. Oh, I've got the secant A, but I need cosecant. Am I okay on that? What is 1 over sine? cosecant. So final step, I change this 1 over sine to a cosecant, and I have the secant of A times the cosecant of A. Questions from anybody? Okay, the last two have some little bit different tricks in them. I'm trying to go through enough that it models the different kinds of tricks you may be needing to use from this point on. Okay, let's start with the left. When I do that, I notice that the left is a fraction plus fraction. And when I add fractions, what am I going to need to think about? Common denominator. So I'm going to leave myself a little bit of space because I know I'm going to need to come up with the common denominators. So I'm going to write the left down, the 1 plus cosine A, and I'm just going to leave some space so I have some room to work. 1 minus the cosine A. Thank you. So if I need to get a common denominator now, that means I need 1 plus cosine A times 1 minus cosine A to be my common denominator. Can't just multiply the denominator. I have to show that I'm multiplying the numerator by the same thing. For the second term, I have the 1 minus cosine A, but I need the 1 plus cosine A. Can't just multiply that denominator. I have to also multiply the numerator. So now my denominators are the same. Let's go ahead and distribute this time. 1 times 1 is 1. And then cosine A times 1 minus cosine A times 1 cancels out. And I'm just left with minus cosine squared A. Everybody good with that for the denominator? Okay, let's write out what we have in our numerators now. 1 minus cosine of A plus 1 plus cosine A. So Emma, what happens with my numerator?
Numerator, you can condense it into, would it just be cosine squared A?
The numerator, if I've got 1 minus cosine A plus 1 plus cosine A, put my like terms together, and what do we have?
Negative cosine squared A?
We're not multiplying the cosines, we're adding them. Minus and plus.
They all cancel out.
And 1 and 1, do they cancel?
No.
They give us a 2. What's the identity you're memorizing today, Ryan? So sine squared plus cosine squared equals 1. Does that help me with this denominator? If sine squared plus cosine squared is 1, what do I get for 1 minus cosine squared? I just have sine squared. I need cosecant squared. What do I know about sine and cosecant? They're reciprocals, not opposites, they're reciprocals. So if I have sine in the numerator or in the denominator, that means I could change it to cosecant squared in the numerator. Questions? All right, our last one. The left side's messier, agreed? So we're going to start with the left side. I've got fractions. What do I have to do when I'm working with fractions, Benjamin? Whether it's trig or anything else, if I'm working with fractions and I want to add them, what do I need? Got to get a common denominator. So again, I'm going to leave myself some space. So I'm going to write down the left side cosine A over 1 plus sine A plus 1 plus sine A over cosine A. I'm just leaving some room to work in there. Common denominator is going to need to be cosine A times the 1 plus sine A. So this one I need to show that I'm multiplying numerator and denominator by cosine A. For this one I have the cosine A, but I need to multiply it by 1 plus the sine of A. So I need to show that I am multiplying numerator and denominator by 1 plus the sine of A. equals. This time I am not going to distribute the denominator unless I get to a point where I think maybe that'll help. Right now I look at that denominator, and if I distribute, I'd have cosine A plus cosine A times sine A, and I don't know of anything right now I can do with cosine A times sine A. So I don't think that's going to help me, so I'm going to leave it factored. If something changes as I work farther through it, I can always distribute it later. Numerator, though, so I'll go ahead and write down that's going to stay cosine A and 1 plus sine A. For this first part, I'm going to have cosine squared A. That's encouraging. We're working with trig squares today in all of these identities. So maybe that's going to help us out. Plus, now I'm going to FOIL this second one. 1 times 1 is 1. 1 times sine A is plus sine A. And then I have another sine A, so I have plus 2 sine A. And then I have plus sine times sine, so that's plus sine squared of A. What is the trig identity that we've memorized? Sine squared plus cosine squared equals 1. Does that help me with any part of this numerator? Ian? Keep looking. I know sine squared plus cosine squared is 1. Yeah, they're just not right beside each other. And just so that somebody reading my proof can tell what I'm doing, I'm just going to put some nice, neat circles around those so they know which parts I'm using. Still want to be able to read it. And then I'm going to say that that equals, and that's cosine squared plus sine squared is a 1. And then I still have this other 1 and the 2 sine A. And my denominator is cosine A times 1 plus sine A. All right, are we getting anywhere? What else can I simplify in that thing? I have 1 plus 2 sine A.
1 plus 1 is 2.
Okay, that's good. The 1 and 1 means that my numerator is now 2 plus 2 sine A. I think I'm seeing some ahas out there. What can we do? Factor out the 2. I think both of you were thinking the same thing at the same time. If we factor out the 2 in that numerator, what does that leave? I don't know. Is that going to help us? Oops, I left out my argument on that part. Good thing I'm proofreading. It's got to have the A. It can't just be cosine. Has that helped? Why are you nodding your head? Yes, Casey. What do you see? So now I have 2 over cosine A. That's a lot shorter. What's left? L, what's left? I have 2 over cosine A. Okay, since cosine and secant are reciprocals, 1 over the cosine A is the secant, so I have 2 secant A, which is what I wanted to prove. So lots of tricks in these problems that we've done today, but I have tried to model the thought process you are going to be using on homework problems and test questions. You are not always, before you start writing a thing down, going to have in your head how the whole problem works. You are going to be looking at it and saying, okay, what is something I can do? Let me write that down and try it. Then you're going to look at that. Did that help? Sometimes you will get to places where it did not get you where you needed to be. Then you're going to look back at all of the steps you've written so far. Where could I have tried something different? And you're going to go back to that place and try that something different and get there. Proofs have a lot of trial and error, and a lot of the time you just kind of have to slowly think through the steps of what's going to work.